Okay, chapter 3.1 is going to explore one-dimensional heat transfer in a cylinder. And cylinders are quite relevant in chemical engineering for the basic geometry of a pipe, but also a lot of our reactors like distillation columns or just a batch reactor, they have a shell that's roughly cylindrical. And so this is a useful geometry for calculating heat transfer. We'll start by defining a cylindrical shell. And here, heat is transferring in the radial direction. And so our differential unit of length has to be in that radial direction. So we choose an increment delta r. And that's going to be our differential length. And eventually, when we start taking the derivative, we're going to be taking a derivative with respect to the r direction. So here's our differential shell. And the first thing we'll do is write Fourier's equation for a cylinder. And it's just going to be that expression we saw, similar to a slab, except that now the heat flow is in the r direction, and our temperature derivative is taken with respect to r. What we need to do is acknowledge that the area through which heat is transferring is changing as the radius increases. It's actually expanding, right? Because the heat transfer area is actually 2 pi r times the length of the cylinder, delta z. So that's the area through which heat is transferring in this geometry. And we substitute that into Fourier's law to get a more applicable form. So that's Fourier's law. Next, we're going to look at the heat equation for a cylinder. And as a note, the heat flux expression doesn't really change except that the derivative is with respect to r. And the flux doesn't change because flux is already normalized by area. So changes in the area don't change flux. All right, so for our heat equation, we'll start by writing out our energy balance, which is accumulation is in minus out plus net generation. And we'll make the assumption that we're at steady state, so our accumulation term can go to 0. And we'll also assume that we have a constant volumetric generation term. And that just simplifies things for us. And it's not a bad assumption. So in that instance, we write out our energy balance, taking care to write the heat transfer area as 2 pi r delta z, and the heat fluxing in is coming in at position r, and it's fluxing out at position r plus delta r. And so the radius at which heat is fluxing out is r plus delta r, and that's why that appears in the second term. And the last term in this expression is the volumetric generation term, and we've multiplied it by a slightly different form of the volume than what you would normally expect to see. It's the differential form of the volume. So 2 pi r delta z is very clearly that outer surface area of a cylindrical shell. And then if you multiply that through by delta r, you get what is roughly the volume of the cylindrical shell. When your value of delta r decreases to 0 in that limiting condition, then that differential volume becomes the true volume. And so this is an accurate mathematical expression. But if you were calculating like a large volume and it wasn't for a differential shell and you wrote 2 pi r delta z, obviously that wouldn't work. All right, so we've got our expression. We divide through by 2 pi delta r delta z. We do not divide out by the r because the r is going to become part of our derivative expression. And also, if you try dividing out by the r, you notice that the term with containing r plus delta r becomes a little bit complicated. And so that should indicate to you that something's incorrect. Don't divide through by the r. And the reason is when you take the limit as delta r approaches 0, what we get is a very tidy derivative of r times q. And you'll notice in this expression we also have an r multiplying the volumetric generation term, whereas for a slab we didn't have anything multiplying that generation term. So this is our heat equation for a cylinder. And in order to insert the temperature dependence, we need to substitute in for our flux Q. So we go ahead and do that. The flux is negative K dt dr, as stated previously. And this expression for the heat equation is correct, and we could use this as is. Sometimes we choose to simplify it. If K is constant, then we can take it outside of the differential, and we've also rearranged the expression by dividing through by r. Both are correct, it's just an algebraic manipulation. And just a reminder, you can apply the chain rule to this expression. So if you wanted to break that derivative into two terms, because r and dt dr are both dependent on r, you can just apply the chain rule and expand the expression accordingly. All of these forms are correct, and so you should choose the form for any given problem that's the easiest to solve. Thank you.